Hello friends, welcome to part 7 of Learn IoT. Well, in this episode we are not going to show you any practical demonstration of anything because we are going to cover some of the basic concepts regarding Internet of Things. Now, in the past few episodes we have seen examples of using end devices. We program the embedded devices. We used MediaTek Linkit as the embedded device platform, and we programmed it and created different applications based on it. Now, in this episode, I'm going to talk only on the communication protocols. In the Internet of Things, the communication protocol is the most obvious and ubiquitous things, right? Because what is all Internet of Things all about if there is no communication, right? So when we talk about the internet, the communication by default comes follows after it. Uh, so in the early 90s and 2000s, we had a lot of embedded devices, and when these embedded devices shrunk in sizes and were came come in the form factor of wearables, there was also a strong need of connecting them to the internet without hassle. So different communication protocols were used. Of course, different communication protocols, different communication channels are having different advantages, different pros and cons. And based on your IoT project need, you need to carefully choose what communication protocol or communication channel best suits for your project. That decision is very much important because if you take a wrong decision on selecting a communication protocol, you will end up having a over budgeted project or a failure IoT project. So to avoid that, the communication protocol selection is an important step. So let's go through it. Before we go to the different communication protocols and channels, let's first understand what is the OSI reference model stands for. Okay. So OSI reference model was basically developed by International Standard Organization in 1984, and it is basically a seven-layer conceptual model. In it describes basically the intercomputer communication. Now, please understand that when we talk about the IoT, here we are talking of one device talking to another device, right? So a device could be an end device, a sensor or a node, and the other device could be your server or a cloud. So there are two physical devices basically which are communicating to each other. It could also be the fact that there are two end devices or two sensors talking to each other in case of sensor nodes or sensor networks. So let's understand the OSI reference model. As you can see that there are seven different layers of a OSI reference model. The first layer is, or the upper layer is called upper layer data. The datagrams are called upper layer data. Then it comes to segment, packet, frame, and bits, right? So let's first understand the top level layer, which is called as an application layer. Now, application layer is basically nothing but a lot of different network applications. So here we are not talking about the applications such as the application that you create, or for example, any let's say talk about your PowerPoint or Microsoft Word. We are not talking of these applications. What we essentially talk about the applications that directly deal with network protocols. For example, a mail, a web browser, okay, or a file transfer, FTP or SFTP clients. Then the network management tools and the remote connections like RPCs or VNCs or different kinds of network connections that we talk about. And because the application is basically on the very topmost layer, it is called as a upper layer data, right? The second comes a presentation layer. Now, presentation layer basically means the data in a presentable manner. So here we talk about more about the ASCII characters. So a data which forms the ASCII characters. That's called a presentation layer basically, right? And it provides a context between the communication layers, and it also does an encryption and decryption. So consider that there is a SSL or TLS implemented. So the decryption at the client side when it visualizes is also done by this layer, or the encryption at the sender side is also done at this layer, right? So the presentation layer is also responsible for making sure the encryption and decryption is in place. It also talks about compression, so there to save a lot of network traffic. It's important that your data is transferred fast from one endpoint to the other endpoint, and in order to achieve that, we had to use sometimes a lot of compressions. So think about some streaming music or streaming video platforms. You ever wonder that how we are able to get a high quality video or audio content streaming over from cloud to our end devices? That happens because of the high level of compression that's happening on the data. So the compression and decompression is also handled in this layer. Then we have the datagrams. The datagrams are basically nothing but the unit of data at any specific level. So the unit of data at this specific level or a datagram is called a upper layer data, which also is the case for application and session layers as well. So the third layer in the OSI reference model in the upper layer data is a session. In the session layer, basically what happens is that whenever there is a communication that need to be established from one endpoint to the other, there is a session that need to be created. All right, and there is a lot of session variables and caches are stored in a session, specific session, and that is why session is very much important. Session is also important whenever a specific communication has to be terminated or a specific communication becomes a stale. So the session handles the state of all the station variables as well, and that's why it's very important layer. So what it does is basically it controls the dialogues between computers. It is also responsible for duplexing and the restart, start, and termination of the communication, right? Again, the datagrams are called upper layer data, which is shared between application and presentation. The next part or the next layer, the fourth layer, is basically a transport layer. Now, what transport layer does? It is responsible basically for transferring the data packets from one endpoint to the other endpoint, right? So, talk about the lowest, transfer protocols like TCP, okay, or UDP communication. So these are part of the transport layer. And as you know that HTTP protocol, the hypertext transfer protocol, is basically derived from TCP, right? So the basic transfer protocols remains to be TCP and UDP in most of the cases, right? This is also this layer is responsible for end-to-end connections. It also makes sure that your connection is reliable. Now, how does it matter basically, or how does it do it? So the transport layer, for example, in case of UDP communication, right? So it's a communication where the data is just sent or broadcasted, okay, from one point to the other, but it doesn't acknowledges the data, right? Or it doesn't wait to get an acknowledgement from the receiving endpoint, right? But when it comes to TCP, then not only that the data is sent from the node, one node to the other, but also the node which sends the data also waits for the acknowledgement that should come back from the receiving endpoint. So the TCP makes sure of the reliability. It makes sure that the acknowledgement is done. It makes sure that the data is successfully transferred and read successfully by the receiving end. It also is responsible for flow control, and that's why it's called segments. So the data grams are basically called segments in this layer. The next layer is network layer. Now this is very important layer because this is basically responsible for transferring your data in a distributed network, right? So from one endpoint to the multiple endpoints or to the other endpoints. It also specifies basically the internet protocols. So whether it is version 4 or version 6, depending on version 4 and version 6, the number of devices that supports basically vary. So IPv4 is for a lot of legacy devices. All your computers and older computers and laptops basically use IPv4 nowadays. Most of the network cards comes with IPv6 support as well. So IPv6 supports multiple IP addresses, many IP addresses basically. And looking at the number of IoT devices that are going to add by 2020, the IPv6 can cater to all these needs. So it supports a large number of IP addresses. Again, these datagrams are called packets here. So You understand, right? The segments are basically a number of packets together. So now packet is basically one packet which will define the header, the payload, and the data, right? So that's the thing. The next data layer is called a data link layer. Now this is essentially where it defines whether it is Ethernet or what is the MAC address of the nodes. So that makes sure that the device, the node device, is identified individually in this layer. Okay, and the datagrams are called frames here. So multiple frames from packet. Then the last layer is basically a physical layer, and this is the bottommost layer in the OSI reference model. Now, this describes the actual physical connection or electrical connection. So basically, think about a chip, okay, and we have different number of GPIOs to it. So basically, it talks about these GPIOs. It talks about the cables. It talks about the connectors, hubs, repeaters, and that's why we work on in this layer. We work on bits. Basically, we are concerned about bits. So basically turning, the 0 or 1 status for a specific GPIO. So that's handled in bits. So this is about the OSI reference model. Now once this is clear to us, we know that how the communication basically gets established. So let's move next. So let's now talk about the IoT protocols. So there are two kind of protocols we gonna learn today. So basically, one is a southbound protocols, and the other is a northbound protocol. Now, what are those? Southbound basically communication is the communication which happens from the middleware or from the gateway to the end devices, right? And the northbound communication is basically from the gateway or middleware to the cloud, right? Or to the entity where basically a data storage or data analytics happens. So in a southbound communication, basically you will see that the protocols that are very prominent are ZigBee. Uh, and ZigBee is very popular because in home automation it's been widely used. The reason because of a lot of advantages that ZigBee has over traditional Bluetooth or Wi-Fi protocols. Then we have Bluetooth low energy, which comes under Bluetooth 5 protocol. Bluetooth low energy basically works on a very low energy devices. So this is more suitable for sensors which runs on batteries. Then we have Z-Wave. Z-Wave, like ZigBee, is a very versatile communication technology, and it is used mostly in the industrial domains, like in factories or manufacturing units. Then we have Dash 7, which is realized by Dash 7 Alliance, and then have Google Thread. Of course, there are many more southbound communication protocols available that you can refer to. For example, some of them which were not listed are like Wi-Fi, and there are so many basically out there. But we're gonna focus on very traditional ones in this tutorial. Then when we talk about the northbound communication protocols, then we have HTTP, the traditional HTTP, which is Hypertext Transfer Protocol. Then we have a secured Hypertext Transfer Protocol, which is called as HTTPS. So MQTT, which is nothing but um, a protocol which basically uh, you know works for with a very, very less payload, right? And then there is a CoAP, constraint application protocol, which is also can be used on the devices where there is a constraint on the memory sizes or the on-chip memory. Then there is a 6 LOWPAN, TCP/IP, and UDP. So let's now uh, talk about the communication protocols in details. So let's start with the RFID, right? So RFID has been there in the industry for quite a long time. The RFID stand for radio frequency identification. Now, how does the RFID works basically? So it uses the electromagnetic fields to automatically identify and track tags attached to objects. Now, what happens is in a RFID there is basically a RFID tag and then there is a RFID reader. All right, and a tag can basically store some information electronically. So the RFID tag will have a very small chip which basically goes and resides in there. and it will have a very small memory footprint where some amount of information can be electronically stored. Usually, the information that is stored in RFID modules is the unique identification number, because the other data that is associated with this unique ID can be stored on the cloud, right? So why this is versatile with respect to the barcodes that have been traditional there for so long years. Now barcodes are very static kind of a type of identification types. Uh, but what happens is for the RFID tag, the tag has to be in the line of sight of the reader. All right, and the tag could actually be embedded in the object itself, so it need not be that the tag has to be a separate device. It can be integrated itself in some device, for example in a packaging itself. And there are two types of RFID tags. The first one is active RFID and passive RFID. Now, as the name suggests, the active RFID basically has a source of energy in the tag itself. Okay, so the RFID's classification as active and passive refers to its classification with respect to the tags. Always remember, not with respect to the reader. So the reader is always powered and it reads the identification number from the tag. The classification of the tags as active and passive depends on whether the tags are powered by battery or not. So the active RFID tags are powered by battery and they operate at also 100 of meters from the RFID reader. So there is no need of a very close proximity of these kind of tags. We could also place it like 100 of meters away from the RFID reader and it could easily be tracked. Then the passive tags are basically the tags which do not have the battery inbuilt, and they depend on the energy that is collected from the RFID reader itself. So when the RFID reader is placed outside and the passive tags comes in a very close proximity with these kind of readers, the RFID tags actually gets energy from the reader, right? And the operating frequencies for the RFIDs basically there are three ranges that we talk about here. So first is the low frequency range where it operates on 120 to 150 kilohertz on unregulated band, which has a range of around 10 centimeter. So it has to have a little bit of close proximity. On a higher frequency on 13.56 megahertz, which you can see a lot of offices will also have the identification badges with on this specific band. So this comes under ISM band on worldwide, and this has a range of around 10 centimeter to 1 meter. And if you need to have a more than 100-meter range or close to 100-meter range, then we go forward to the ultra high frequency range of the RFID devices, which comes under 433 megahertz. So, what are the advantages and disadvantages of RFID? As you can see that in the pictures, I'm showing some of the examples of active RFID and also how the RFID, tags are basically made up of. So basically, RFID tags has an antenna in terms of a coil, right? And then there is at the center you can see a small chip, which is basically stores some sort of an electronic information such as an identification number. So the advantages of RFID basically that the RFID tags are very easy to install. You can either incorporate them into the device itself, or you can, paste it on top of the devices, or you can embed it in the device itself. Also, it can store up to 2 kilobytes of data. So apart from just a unique identification number, some sort of a custom information also can be stored, which should not go beyond 2 kilobytes. So it's a very low memory device, which is an advantage for it. The RFID cannot be replicated easily because it is, tagged with a unique identification number. So it is very difficult to tamper with by the hackers. So it is more secure. But what are the disadvantages? The disadvantage is basically is that because it works on the radio frequency. Now you need to understand when it comes with the fact of radio frequency, then the radio frequency properties are altered a lot with fluids and metals, and that's the reason the readers then find it difficult to read when there is a lot of fluid or metallic environment around the tags or the reader. Another disadvantage is that it's an invasive technology, which means it is visible. it's not ubiquitous. It is visible to the eyes of the people. It is very difficult to also, put it. Although there are some devices which can actually get embedded, but definitely for the active RFID tags, it is pretty much invasive. And then also different countries have different frequency ranges because of the regulatory parts. So it will be very difficult when you have to have, use it across the countries. Then it's quite difficult to manage the RFID as a communication protocol. Then what are the use cases of RFID? Even though RFID has some advantage or disadvantages, still in today's lives, we are using RFID to certain extent. So where are we using them? We are using them for people tracking. Because it's quite easy. Basically, we can attach the people with active or passive RFIDs, and we can install readers at different places. By using the triangulation method, we can identify the location of the people, and we can plot it into a remote system in a map, or in a certain application. Then school bus tracking is one of the good example where each child can actually go along with his individual RFID tag, and the reader installed in the school bus can continuously track the presence of the kids. So they can also monitor where the kids are getting dropped in, whether the kids are getting on board the bus or not. So everything of that solution. Uh, what is ubiquitous even in today's lives for RFID is basically the parking solutions, or even in the toll plazas. You can see that the tags that are attached to the windshield of the car are basically the passive RFID tags, and the every parking lot or a toll plaza will basically have a reader which will continuously transmit a radio frequency and will collect the information. Now, based on the identification number that is received from the tag, it identifies whether the car is permitted to go into the parking lot, or having a sufficient balance to cross the toll plaza or not. So that's a very best solution you can see across all countries using this solution for their parking or toll plaza solutions. Then in the retail and inventory tracking, also some of the retailers are using the RFID tags as managing. You can see that most of the time a plastic tag is attached to clothes, and that is only removable by certain methods. So when a person is basically trying to carry the specific item which is for selling outside of the retail store, the readers basically identifies that and gives alarm. So for security purpose, or even for inventory tracking, the retailers are using it. And then for supply chain management, for example, the tags could be attached to a package, or on a carton box, and the carton box can be tracked from its source to its destination, from the factory to the retail store. So the whole supply chain management can also be achieved with the help of RFIDs. Then in healthcare, identifying the patient's location, identifying the instruments location, the location of the stretchers, the location of the wheelchairs, this can be easily achieved in the medical centers easily. So healthcare is also one of the best domain for RFIDs nowadays. The document trackings, we can use the passive tags, and a movable reader can be swipe across the documents to identify if the specific documents is there or not. So it's very easy to easily identify and get the document which a person needs to assess at that point of time. In the manufacturing also, most of the times, for to control or regulate the process, the bins or the trays will have the RFID readers, and they could be traced from one point to the other point, making sure that the product goes through definitive process cycles. So manufacturing also has a lot of advantage for RFID. Then the next comes the near field communication. Now near field communication is basically an assistive technology. So what NFC does basically is that it enables two electronic devices. One of which is NFC enabled, for example, a smartphone, to establish a communication by bringing them with a close proximity. Now you would see that a lot of smartphones are NFC enabled, and you would see that, for example, one of the best case am explaining you is there are NFC speakers around. So what we usually have to do is basically get our phone which is NFC capable, and tap it near to the or tap it onto the NFC enabled speaker, and what happens is then the Bluetooth communication automatically happens, and the mobile can start streaming the music to the NFC speakers. So it's an assistive technology. Again, the NFC could be active or passive depending on the configuration. The passive devices such as NFC tags also contains information which can be read by reader, right? And active devices can read information and send it, for example, smartphone. So you can see some photographs here that there are NFC enabled tags, and there is also an NFC enabled payment option is also available. So if your smartphone is having already an NFC and you have some wallet application installed, you can actually do the payment with just an easy tap on the NFC enabled payment readers. Advantages, disadvantages, of course, advantage pretty much easy because no manual configuration and setting is required. It's perfectly fine. You just need to purchase the readily available product and just use as it is. No technical know-how is required also by the user. Also, devices can be configured or paired quickly because it works on a very close proximity. So again, no know-how is required. It's a secure communication, and setup time is less than zero point 0.1 millisecond, which is quite healthy. Whereas the disadvantage is that the data transfer rate is very low, so it cannot be used for a very huge data communication, applications. And also the range is very short; it's 10 centimeters, so it has to has a close proximity, and that's the reason it cannot be used in applications where you need to have a longer range and higher data communication. What are the use cases of NFC? Of course, we saw one example of e-commerce. A lot of NFC enabled phones like smart Samsung or Apple, they have NFC enabled. So NFC can help to do securely the payment for your purchases at some retailers or at shops. Then bootstrapping other connection. For example, uh, consider a Bluetooth speaker that I talked about, right? So you just get your NFC enabled phone near to the NFC enabled smart speaker, and you just tap it, and then the Bluetooth communication just happens automatically. So it actually bootstraps NFC bootstraps the Bluetooth communication, right? So bootstrapping other connections. Social networking, you can see that there are a lot of NFC tags placed in malls, offices, and different public places. You just have to tap your phone on this tags, and you can get certain information. For example, the know-how about the place, the offers that are going around in the mall, or it can also quickly connect you to social platform. For example, you can create your NFC enabled smart tag with your information. For example, uh, uh, your name, your mobile number, your website, your Facebook or your LinkedIn profile, and you can just instead of exchanging your visiting cards, it's like NFC enabled visiting card. Instead of exchanging visiting cards, you can just ask the user to tap on your tab, and your information can get transmitted to his phone. Then there are ID and accesses for which also NFCs are used, although not that popularly, but of course it can be used. There are also smartphone automation that you can do. Now, one of the best examples that I see for smartphone automation is basically handling the scenarios. So let's consider that I have a one NFC tag at home, right? I'm keeping it at on my tripod or a table, right? And one NFC tag in my car. Now, when I come home, I can just tap tap my phone on the NFC tag. Now, what happens is that the NFC tag could be pre-programmed to activate certain modes in your mobile phone. So, for example, when I come home, I do not want anybody to call me, right? So I put it on a silent mode, for example, or I can play a music, so I can program the NFC tags accordingly. And as soon as I tap my NFC phone near to the tags, it activates that specific mode. Similar thing happens when I get into the car. For example, I just tap it onto the NFC phone tag, and what happens is that the Google Map comes up, and it starts navigating me to where I want to go, or it can start playing some music. It start detecting the routes, navigations, etc. So smartphone automation can be easily done with it. There are also gaming applications there in NFC which are limited now, but there are still available which you can explore. Now the third technology that we're going to see is the Bluetooth. Now Bluetooth is there around, with us for a long time, pretty long time. A lot of our, basic entry level mobile phones also came with Bluetooth, and Bluetooth was a very good communication uh, uh, media on in the initial days. Even today, we have a lot of Bluetooth enabled devices such as the headsets or gaming controllers or laptops, mobile phones, PDAs, printers, So this is a open standard for development on a very personal area network, and it is a very low cost, low power, and a short range technology. So very good for in-house IoT applications. Now, the Bluetooth protocol stack is quite easy, as you can see, right? So the green part is basically the Bluetooth core protocol, right? So it has a Bluetooth radio, baseband, LMP, and L2 cap. Then there is an adopted protocol which has UDP, TCP, and communication protocols implemented. Then there are cable replacement protocol like RFCOM, and then there is a telephony protocol. This is simple Bluetooth protocol stack. Now, what are the Bluetooth pros and cons? Like Bluetooth is definitely being around here, but in the recent days for the IoT application, it may find some disadvantages. So the advantages are very obvious because it is an ad hoc connection, right? Secondly, it works on a 2.4 gigahertz frequency, and 2.4 gigahertz is identified as a global, worldwide frequency. It is identified in every country that it operates. And on 2.4 gigahertz, we find many other protocols also like Wi-Fi, ZigBee, Z-Wave, right? So it's a universal frequency, so can be used in every country. Then Bluetooth, yes, it is implemented by a large number of companies, not only companies, but also a lot of individuals are using Bluetooth. It is also suitable for creating a piconet, a sensor network of a small devices. But the data disadvantage, again, low data rate because it's a short range, and also it cannot handle higher data rate. So for a very small amount of data transfer, it's okay. But think about if you want to do a streaming of video or audio, definitely Bluetooth is not a good communication channel for that matter. Then also it is prone to interference from other devices working on the same band. So if you have many multiple Wi-Fi devices or other devices which works on 2.4 gigahertz, it might get interfered with those devices as well. It is short range, so you can use it for purposes where you need to cover a one living room or maybe a living room and a bedroom. But then if you have a large houses or companies or offices, then the Bluetooth definitely has a pitfall. And also it is having a higher power consumption. So you would see that the Bluetooth devices need to be charged again and again all the time, at least every alternate day, right? So that's why it's a higher power consumption. To overcome some of the disadvantages with the traditional Bluetooth communication, uh, there was a development done for a BLE. Now, BLE stands for Bluetooth Low Energy technology, right? And the Bluetooth Low Energy basically works from Bluetooth version 4.0 specification onwards, and currently we have Bluetooth version 5.0 also available. So a lot of the headsets and devices, the sensors, IoT devices that are coming with BLE, even the BLE also supports now mesh, so you can form a mesh of different BLE devices which can talk to each other. Now, some of the disadvantages that we had with the traditional Bluetooth, for example, a higher battery consumption, was avoided with the introduction of a Bluetooth Low Energy. It is very low cost, so you can see that a lot of Bluetooth dongles and small Bluetooth devices basically are working on a BLE technology. BLE stack is as in front of you. Basically, there is also a physical layer, link layer, direct test mode, which forms a controller. There is a host, and then there are application on top of it. Pros and cons. Of course, the advantages for Bluetooth is basically there is a high data rate, so you can definitely stream audio, music. Streaming is very much possible. Uh, it has a low power consumption, so it can operate on a small battery and for a long amount of time. It has a medium range, so you can go up to 200 feet. So with a BLE, you can definitely cover up all your requirements for a one specific standard home, right, with multiple rooms. and it is also implemented by a large number of companies. But the disadvantage basically again, interference is possible from other devices. The initial setup time is more, so it's quite difficult to not difficult, but you need to spend a little bit of time, and you need to have some sort of a knowledge base in order to do an initial setup for Bluetooth devices. And Bluetooth tags are very expensive, and it requires still a power. Now, what are the use cases? So, use cases basically where proximity, time, network availability, personal user interface, simple remote control, Bluetooth-based remote controls there, browse over Bluetooth, temperature sensors. There are a lot of temperature sensors, humidity sensors that work on Bluetooth. There are HVAC controls, HVAC systems that are working on Bluetooth. Generic IO automation we can do with Bluetooth, right? Battery status, heart rate monitor, physical activity monitor, blood glucose monitor. So you can see a lot of smart watches or the activity trackers. They are also coming with Bluetooth. Then the next comes ZigBee. Now ZigBee, as we talked in the initial discussion, the ZigBee is very much good for the home automation or smart home automation. Now, why it is so popular for home automation? Because of some of its specific advantages. First of all, it's a low data rate. And in home automation, for example, sensors and different nodes, they do not have a huge amount of data, right? So they talk about with a very small payload or small data. So low data rate is perfectly fine. It has a very low power consumption. It has a small packet devices. It operates in unlicensed bands on a 2.4 gigahertz global band, so it is acceptable everywhere. Although there is also an European band which is sub gigahertz, which is 868 megahertz, and there is also 915 megahertz, which is North American band at 40 kbps. So there is a different data rates. At 2.4 gigahertz, you can achieve the highest data rate, and which is the most widely accepted frequency range because it is universal. Then ZigBee models with different ranges are also available. We can get a ZigBee model as low as 30 meters to as high as 2 kilometers as well. And then it also supports multiple topologies. For example, mesh star one to one. Now, what is mesh star one to one? So mesh is basically where every device in the group communicates to every other device, right? So you can see this device communicates this device again communicates to this. So every device communicates to every device, which is called a mesh. In star, there is one device which then communicates to other devices. So it forms a star-like topology. And then there is one to one, which means one device talks to another device. That's it, one to one. For example, there is a ZigBee gateway, and then there is a sensor or a node which only they talk to each other. So as we mentioned, right? So there is a star, then there is tree, and then there is mesh. In a mesh topology, you can see that there are different coordinate, etiquetators, end device, and routers. Now, what are these basically? So coordinator is nothing but a gateway, a ZigBee gateway, right? So coordinator aggregates all the data and is basically responsible to upload that data on a northbound to cloud, right? Whereas the router devices are basically the devices which will require a little bit more power than the end devices, but will also will be able to communicate with multiple devices. So they can communicate over the network in a mesh network to other devices also. So it can communicate with other routers or other end devices, multiple end devices. Whereas a end device is basically a very low battery consuming device, and it can communicate with only one other device, which is either a coordinator or a router, right? So IEEE 802.15.4, why we are talking of here? Because ZigBee is basically defined by this specification, right? So we talk in this specification, we talk about a small packet size, which is 128 byte. It uses a 54-bit MAC address, but also has a provision for 16-bit short address. It supports multiple topologies, for example, mesh, star, and tree, as we saw seen. It also supports AES encryption, so it makes it secure. Even the communication on the ZigBee protocol is secured by AES 256. Data rates are between 20 kbps to 250 kbps, and depending on your application, you can choose uh, the devices with different data rates. and it can give you the range between 10 meter to 30 meter. Now, when we talk about the range, basically, and we go back to this topology of, the mesh, the range is not a problem when it comes to mesh. Why? Because the mesh basically extends the range. For example, what happens, consider this is your coordinator, right? And then this is a device which is configured as a router. Now, what happens is that this router is in the mesh network. So what it does is, initially the ZigBee coordinator has a range of, let's say, 100 meters. Now this ZigBee router becomes a, a device which can again form a 100 meters radius. So it extends the range by another 100 meter. As many devices as you add in the mesh network, it extends range beyond its capability. So range will not be a problem in ZigBee. So when we talk about the OSI reference model, again the same model has been also used in ZigBee. And as you can see that the ZigBee is strictly, managed by the ZigBee Alliance, all right? And the ZigBee Alliance is basically responsible about the software part, the network security and application layer, right? So this part of the OSI reference model is handled by ZigBee Alliance, whereas IEEE 802.15.4 defines only the MAC and physical layer of the ZigBee protocol. Again, advantage, disadvantage. Okay, there are many advantages as it is low power, right? It supports multiple topologies based on your application. You can select mesh, star, one-to-one. The communication range is long. It can support up to 1.5 to 2 kilometer range. The nodes can be scalable with little configuration. Then disadvantages are basically that it has still has a low data range, 250 kbps, so probably not good for applications where you need to have a higher data rate. It is also expensive. ZigBee is not so commonly used. So if you compare them with Wi-Fi devices or Bluetooth devices, you will find that the ZigBee chips are quite expensive, around $4 to $5. The frequencies other than 2.4 gigahertz requires licensing. So uh, because 2.4 gigahertz is on the unlicensing terms, it can be widely used. But when it comes to a sub gigahertz band, as we saw in the new European North American, this would require the licensing in those countries. Use cases, well, there are many use cases, but if you just talk about the very top level use cases, then there are four. First is home and building automation. I think this is the best protocol so far which can be used in home automation. If you are thinking of developing some IoT system for homes and offices or buildings, I think ZigBee is the best suited protocol for it. If you fall for Bluetooth or a BLE, I think over the period of time these will get obsolete for use in homes and building automation. So ZigBee is definitely a very standard protocol to be used in home and building automation. Wireless sensor network, as we discussed, because it supports a mesh topology. When you want to form wireless sensor networks in specific areas, I think the ZigBee is one of the best protocol that can be used. In medical data collection, you can actually attach it to the patients or to the different sensors or devices. So medical also finds a lot of use cases. In the industrial control and manufacturing, in the HVAC offices, you can see a lot of industrial places, its use cases. Then comes Z-Wave. Z-Wave is similar to ZigBee in a lot of ways, but Z-Wave is primarily used in industries. So as you can see that it is also oriented towards residential and automation market, but mostly widely used in industrial thing. It works in sub gigahertz frequency band, 900 megahertz and 100 kbps, and can have a maximum of 232 nodes. So you can connect 232 devices to one coordinate, Z-Wave coordinator. Again, like ZigBee Alliance, the Z-Wave is managed by Z-Wave Alliance, which is a consortium of different 300 plus manufacturers, which who manufactures Z-Wave based chipsets or devices. It also operates on mesh network architecture, and the USP for Z-Wave is its interoperability. So why interoperability? Because if multiple manufacturers are using Z-Wave as a communication technology, they can be interoperable. So you can, for example, buy a Samsung ZWAVE appliance and can be able to communicate with LG branded ZWAVE device, so which is quite possible. When we look at the advantages and disadvantages, so the advantages of Z-Wave are basically it's ultra low power consume. It has a low latency, so it's very fast. It forms a reliable wireless communication protocol. It supports mesh topology, and this system greatly extend its range. And also it is for ideal automation. Whereas the disadvantage, when we talk about, it still has a low data rate of around 100 kbps. Also, limited number of nodes can be connected per network, and that's the reason it's not that perfect. Use cases, again, home automation. We talked about in ZB, we'll not repeat it. Medical applications, similar kind of applications. Simple remote control. There are a lot of Z-Wave enabled remote controls are available. So because it being wireless, it's quite easy to communicate. So you can define different scenarios. For example, on touch of a button you can execute a specific scenario for home automation. So a simple remote control application can be formed. And the gaming. Then there is a 6LoWPAN. Now 6LoWPAN is a simple low cost wireless network for devices that have relaxed throughput requirements. Now this also comes under IEEE 802.15.4 standard. And as you can see that there is a OSI reference model that defines it. Uh, there are a lot of advantages of 6LoWPAN because what happens in 6LoWPAN is it uses the IPv6 uh, in in a wireless personal area network WPAN. So 6LoWPAN, which means IPv6 over low power wireless personal area network, right? And it can be used with IoT devices which has a very constrained hardware, and it can be used for applications where longer range is required. So even in smart cities or smart meters, a lot of advantages are there in using 6LoWPAN. This is a routing in 6LoWPAN, as we can see. What are the pros and cons of 6LoWPAN then? The advantage is basically is the low power again, so less consumption of energy, less physical layer overhead. So that's why the packets are very small, low cost, and more suitable for higher density networks. So that's why we said that a smart city could be a best example for 6LoWPAN. Whereas the disadvantage are basically the IP and higher layer packets may not fit in one frame, hence not suitable for large payloads. It is again short range, 30 meters to 10 meters to 30 meters, and it is having a small packet size, only 128 byte, which includes MAC and 103 bytes of payload. So you can put a lot of payload in a small packet size, and it complies to IPv6 node requirements. Use cases, as we see, smart grid. So this can easily be used in places wherever you want to use smart cities or smart meter technologies. It can also form a wireless sensor network. It can also be used in industrial automation, and it can also be used in advanced traffic management. So places, outdoor places, noisy environment places, 6LoWPAN is a better option for these kind of a noisy environments. Then comes Google Thread. Now, Google Thread is Google's proprietary, communication protocol. So it is basically for connected home requirements. So Google had introduced it for its own Google branded appliances. So as you can see that what are the devices that supports Google Thread? So there are normally powered like normal electrical AC voltage, so there are gateways, lighting, appliances, smart meter, HVAC, smart plugs, fans. Then battery powered, there are thermostats, light switches, doorbells, glass break sensors. And then there are normal batteries where door sensor, window sensors, radiator valves, or door locks will come. Again, uh, Google Thread can form a mesh similar to as shown in the diagram here. And as you can see that it's different layer. So you will have a physical MAC layer, and it uses a 6LoWPAN as a communication technology, which then routes to UDP, where on top of it you can build your applications. Communication channels. Um, there are three basically: a service provider. The service provider is a company that offers communication services to the users. The network protocol are basically a formal standards and policies, and the communication channel is basically the hardware media, for example, a wired Ethernet or a Wi-Fi or a coaxial or a fiber cable. So in the communication channels, when we talk about communication channels, we will cover up these four most widely used communication channels. So the first one is cellular. Now, cellular has been there since olden days when with the introduction of mobile phones. You know, so we had somewhere 2G, the second generation, which includes General Packet Radio Service (GPRS), Edge, and Code Division Multiple Access, which is CDMA. With the introduction of 3G, then we have WCDMA, wideband CDMA, we had UMTS, we had HSPA, HSUPA, HSDPA. And in 4G, then we have long-term evolution, LTE and LTE for IoT. Then the another type of communication channel is a Wi-Fi, which is widely used in every home nowadays. Then there is a Sigfox, which is very specific to European markets, and then there is LoRa, which is long-range communication channel. So let's cover up cellular networks now. Cellular networks are basically from first generation to fourth generation right now. Of course, we are now talking of 5G enabled networks, but still we don't have any commercial use case right now. So we'll only cover up to 4G. So the first generation wireless cellular was introduced in early 1980s. It had analog transmission. So basically, the only primary use that time was the speech communication. Uh, so the speech was modulated and demodulated with the first generation network, which was called AMPS. AMPS stands for Advanced Mobile Phone Systems. Then there was a need of data, and then there was an introduction of a second generation wireless cellular, which came in late 1980s. Now with this, we transform from analog transmission to a digital transmission. So the analog transmission was converted to digital. A lot of samplings were done. It was for primarily for speech and a very low bit rate data. Okay, and the bit rate that we were talking of was around 9.6 kbps. With a high tier GSM, IS-95 CDMA came, and then with a low tier PCS. With the introduction of 2.5G, the 2G evolved to medium rate. So the only difference between 2G and 2.5G basically was the enhancement of data rate from 9.6 kbps to less than 100. The 3G third generation wireless cellular came, which was introduced with the introduction of wideband CDMA. It introduced the data rate of 144 kbps to 384 kbps, and it had a high mobility and high coverage as well. Then there was also 2 Mbps communication for low mobility and low coverage. And today, I think most of the countries already have 4G, which is a fourth generation wireless cellular, which was introduced in 2009. And I think by 2018, I think almost every country today has LTE bands available for every network operator that we see today. The peak download can go up to 100 Mbps and peak upload can go up to 50 Mbps. So you can see that the data rate has been uh, exactly enhanced from 1G to 2G to 5G, 4G. There was no data in 1G. Cellular networks is the underlying technology for mobile phones and personal communication system, right? And it was primarily developed for but why it is called cellular basically because when we talk about these networks, they form cells. So there is a mobile station, right, or a base station that we call it, and one base station actually covers a uh, circular or maybe more like an elliptical or circular kind of a cell, right? So with the introduction of multiple base stations, we form different cells, and whenever a user moves from one cell to the other cell, then there has to be a handover from that cell to the next cell. So that's why it's called a cellular networks. As you can see that this is the cellular network architecture. So you can see there are many BTS, okay, base stations that are called. This forms a cell. Now, why this shape has been shown as hexagonal? Because when you have overlapping circles, you can see that the endpoints that you connect with the overlapping circle will form a hexagonal. So the BTSs basically covers each cell, and if all the BTSs are connected to a specific base station controller, which is called as a BSC. Okay, so one BSC can serve to multiple base stations, and then multiple base stations can be connected to a MSC, okay, mobile switching center, which then forms a data network. Um, all right, so we have seen also 2G and with the GPRS. Basically, GPRS was a general packet radio service. GPRS was a packet-oriented mobile data service. Okay, uh, and with the GPS, people in the early 80s started having the internet communication, right? So people could access the text over the internet or some imagery over the internet. The data rates were very low. With the introduction of edge, there was an enhancement of a data rate, so people could basically use a lot of mapping applications also, because the data throughput was up to 64 kbps to 384 kbps. So edge could basically bring a lot of navigation and mapping functionalities. With the introduction of CDMA, CDMA stands for Code Division Multiple Access. So basically, how does CDMA works is basically consider that there are 10 people which are in the room, right? So there are five who speaks English, two speak who Spanish, two speak Chinese, and one speak Russian, right? So now if everyone is talking at relatively some time, same time over the same medium, okay, which is air, then you can tell me that who can listen to whom and why, and who can't you understand, who can't speak to anyone. So you know that if you know only English, right, so you are one of the English person who doesn't understand Spanish, so you'll easily ignore the Spanish thing, but you can easily interpret the English. So basically you split the time in different codes, and you only accept the code that you understand. Right. So we'll just keep this, and then we have 3G. With the 3G, then the throughput or a data rate was enhanced even further with 144 to 384 and to up to 2 Mbps also. So 3G introduced us to the short message services, the MMS, the streaming audio, video, multimedia things. Then we had 4G, okay, which introduces us to the next generation mobile broadband technology, right? With the LTE basically refers in 4G as long-term evolution, right? And is a standard for wireless communication for high-speed data. But a marketed name is called as a 4G wireless service. So you can see that from 1G, the data rates have been extremely enhanced. 1G had tax, 2G introduced us to GSM, GPRS, and Edge. With the introduction of 3G, we had WCDMA, wideband CDMA, high-speed packet access, and HSPA plus. And then with 4G, we have long-term evolution. After this, it comes LTE for cell. Has and which is quite sufficient or quite good for IoT application, because in case of IoT there is a huge amount of data that is produced. So we require a communication channel which can withstand that sort of a data. So that's why for LTE for cellular IoT has been introduced. It is also used in machine to machine communication as well. Now, talking of Wi-Fi, I think Wi-Fi has been with us for quite a long time. It's a technology that is ubiquitous, which is seen everywhere. Everybody is using that. Wi-Fi is there in everybody's personal computers. You can find it in video game consoles, in smartphones, cameras, computers, printers, video players, audio players. So Wi-Fi is less secure than wired because, of course, it can be tapped unlike the physical Ethernet communication for IP. For that you need a physical communication. But when it comes to Wi-Fi, it can be easily tapped, so it is less secure than wired communication. And there are five frequency ranges around. So there is 2.4 gigahertz, which is most widely used in today's world. There is 3.6 gigahertz, there is 4.9, there is 5 gigahertz, and 5.9 gigahertz. Nowadays, you will see that most of the routers that you purchase newly will come with 2.4 gigahertz and 5 gigahertz as dual band routers. As 2.4 gigahertz is becoming extremely, uh, you know, congested, people have started using 5 gigahertz band as well. So there are Wi-Fi pros and cons. Advantages: Wi-Fi is very low cost. You can get Wi-Fi chips for a very less cost, around 50 cents to a dollar. It can be easily installed. It is scalable, but it is also less secure. Well, the disadvantage is high power consumption. If you compare the Wi-Fi against ZigBee or BLE, it consumes a lot of power. So which means that you need to charge those devices very often, or you need to have sensors or IoT devices which are plugged or hooked to the power source permanently. Again, interference from other devices, because it works on 2.4 gigahertz primarily, and there is a limited range. So consider that if you are trying to consider Wi-Fi as a smart home automation technology, it will not be proper to use it, because as you know that most of the times in bigger houses or bigger offices or bigger buildings, the Wi-Fi cannot reach to multiple rooms. In that case, then you need to use a Wi-Fi repeater, which means an additional investment for it. So range is one of the disadvantage. So when you talk about range, I think the the most probable solution, if you want to go for a very high range, is LoRa or a LoRaWAN. So LoRa stands for long range, and it is a spread spectrum technology with wideband. It usually works on 125 kilohertz or more. Its frequency modulated chirp utilizes coding gain for increased receiver sensitivity. Now, LoRaWAN defines a communication protocol and system architecture for the network, while LoRa physical layer enables a long-range communication link. You can see that the advantages that LoRa offers are basically the battery lifetime of a node, the network capacity, the quality of service, security, and it can be used in a variety of applications. But it has a maximum data rate of 50 kbps. So although LoRa has a long range, which goes up to kilometers, but the data rates are still lower, 50 kbps. But it can be used in applications, in IoT applications where data rates are not going beyond 50 kbps. Also, LoRa has a 10 years battery life. So with respect to a battery saving, I think LoRa is the best option. Sigfox. Now, Sigfox is a narrow band or ultra narrow band of 100 hertz technology. It uses a standard radio transmission method called binary phase shifting (BPSK), and it takes very narrow chunks of spectrum and changes the phase of the carrier radio wave to encode the data. Sigfox wireless systems send very small amount of data, 12 bytes, very slowly at 300 baud using standard radio transmission methods. The long range is accomplished as a result of a very long and very slow messages. So the messages, as we said, that are very slow and very long, so it can actually traverse to a long range. The technology is good fit for any application that needs to send small, infrequent burst of data. Things like basic alarm system, location monitoring, simple metering are examples of Sigfox. But there are limitations also in Sigfox. Sigfox service providers has not deployed any bidirectional network. So it's only unidirectional communication as of now. The signal is typically sent a few times to ensure the message goes through. So that basically adds to a lot of latency as well. And then there is a fixed packet size of 12 bytes, which is very small. So when you compare Sigfox versus LoRa, so let's see how they comparatively they perform. So when you talk about throughput, the Sigfox has 100 bps to 300 bps throughput, but LoRa has 300 bps to 50 kbps, which is higher than Sigfox, so better. Packet size only 12 bytes in Sigfox, but LoRa can go up to 256 bytes, which means more data can be fit into the single packet. Payload only 10 bytes, but whereas the payload in LoRa is 51 to 222 bytes, so which efficiently uses the uh, the entire packet for most of the data. Bandwidth in Sigfox is 100 hertz. As we talk, it's a narrow band, whereas LoRa has a bandwidth of 125 kilohertz. Uh, Again, the range for Sigfox is 50 kilometer, but it can go up to 50 kilometer, which means it can actually cover up a small town, whereas LoRa can go up to only 20 kilometers. So only for a small community or small place or small island it can cover up. Uh, Whereas Sigfox is only unidirectional, LoRa is bidirectional. So LoRa wins in uh, the directional sensitivity. So that's it, all about communication technology. I think when you will learn these communication channels, you would be easily, help yourself in identify the right communication channel for your IoT project. Now, it is very essential to select the right communication channel for your project because you need to consider a lot of different parameters. Now, why we talked about the advantages and disadvantages of each communication channel or a technology? The reason basically was to identify what best fit for your project. So consider that, like ask yourself a question. For example, if you want to create a home automation system, which communication channel will use? Well, your answer should be either ZigBee, ZWAVE, or BLE. Okay. When you talk about smart city project for an entire town, which communication technology you might prefer? So your answer should be either LoRa or Sigfox. So ask yourself these questions and go through the advantage and disadvantage of these communication channels carefully. You will identify easily what communication channel best fit for your project. That's all, folks. I think there are many more communication channels available. I would like you to, comment on this tutorial and let me know what communication channels you are more interested into, and we might cover it up in our next episode. Also, you can give us a feedback that if you find something missing or something you need to add up, you can definitely comment this video and let me know so that we can cover up it in the next tutorial. For time being, thank you very much.